Since the first human space mission in 1961 to the most recent space expeditions of the decade, NASA has been recognized as a world leader in space exploration. With over 50 years of success, NASA has been responsible for the development of our knowledge about space travel. Today, NASA conducts many experiments in space, one of which is the Reversible Figures Experiment.
The Reversible Figures Experiment is a recent experiment that flew aboard the International Space Station. It was intended to measure any changes that might occur in depth perception in astronauts in space.
Designed by Dr. Gilles Clement, Dr. Bob Thirsk, Tahir Merali, and 9 other graduates from the International Space University, the experiment made use of special images called reversible figures, which could be perceived in one of 2 ways by an individual.
The hypothesis for the Reversible Figures experiment was that in space, over a period of time, our perception of depth and our perception of reversible figures might be altered in the absence of gravity.
Conducted on board the International Space Station by 6 astronauts, the astronauts were instructed to wear head-mounted devices in which they could view 2 different sets of reversible figures.
In the first set of figures, they were drawings of 3-dimensional objects. So for example, of a cube on a table or hanging in the air.
As a control variable, a second set of 2D figures, which could be perceived in one of 2 ways, were also shown to the astronauts. As their perception of the objects changed, the astronauts recorded the frequency of image reversals.
The astronauts performed the experiment several times, 3 times before flight, 4 times during flight over a 5 to 6 month expedition in space, and then 3 times after flight as well.
For control subjects, Dr. Thirsk and his colleagues selected 14 students to conduct the same experiment on Earth. These results were great comparisons to the data collected by the astronauts in space.
There are multiple phases to the Reversible Figures experiment, and these are similar to phases of other experiments that are put onto the space station. There is the development and creation phase, which is where we design the experiment and understand what it is that we want to find out, determine our hypothesis. Then there is the physical design of the software, once we've decided what we want to use.
The results of our experiment showed us that, as we expected, on Earth, both the astronauts and the control subjects tended to see each of the reversible figures predominantly in one way or one view.
For example, when subjects looked at the Necker's cube on Earth, they predominantly saw it sitting on the ground 70% of the time. For the other 30% of the time, they saw the cube in its other view as hanging in the air.
What was surprising was that in space, they began to see the 2 views from each of the reversible figures about equally, 50-50 or so.
Due to the absence of gravity, our perception of orientation is dramatically minimized. This affects our ability to perceive depth and distance due to the absence of a gravitational field.
If you are using the Canada arm and looking through a window, trying to gauge distance about how you're trying to capture a satellite, this may be something that could cause some issues.
It's critical that we have a good 3D impression of where that arm is in space. We don't want to move the Canadarm2 if it's close to space station structure for fear of damaging the arm or damaging part of the space station structure.
The most obvious countermeasure that could be used to help astronauts cope with the impact of illusionary depth is assigning an orientation.
To achieve this, scientists use certain colors inside the space station to help the body understand what is up or down.
For example, you could use blue to indicate sky and brown to indicate soil, which would inherently understand to the body that, hey, one is up and one is down.
The Reversible Figures experiment took approximately 5 years, from the design of the experiment to the publication of the results.
We were very fortunate that nothing major went wrong with the Reversible Figures experiment. This is really important, that an experiment for space is well planned, that the hardware is robust and well designed. Because often in space, a scientist will only have one chance to perform their experiment. But Reversible Figures was well designed, it was well planned, the hardware was good, and we had complete success.